Okay, good morning everyone, and thank you for joining the class today. We'll do lecture 15. And before we start, if you remember last class, we spoke about the matter and the properties of matter. And we've mentioned that matter is anything that has a mass and occupies a space. Anything that has a mass and occupies a space we call a matter. And we said that the matter could have either physical properties or chemical properties. And we mentioned that the physical properties have more to do with the shape, size, volume, density, roughness, and so on. And the chemical properties have to do with the chemical structure of the matter. So if there is any change in the chemical composition, that's what we call a chemical property and a chemical change. So today what we're gonna do is we will go inside the matter, see what is going on inside the matter. So I will go to the microscopic level and even lower than the microscopic level and see what is going on. So we'll speak about the atom and the structure of the atom. Now, before we start, we have to learn about this table, which is called the table of elements. So here you can see a group of elements. You can see aluminum, calcium, carbon, chloride, gold, hydrogen, iron, mercury, nitrogen, oxygen, potassium, sodium. And you can see each element has its own chemical symbol. And as you guys know, from our study before in high school and so on, we've learned that we in the periodic table that each element has its own chemical symbol. Now, how can I name elements? Sometimes I use the English name, like for example, the aluminum, so I use the first two letters of the English name, so it's Al. Calcium is Ca, carbon is C, chloride, Cl, and so on. And sometimes for the elements that had been discovered for so long, like the iron, like the hydrogen, like the mercury, we use the Latin name. Like for example, I don't call gold G, but I call it Au because the Latin name is Urim. And for example, the iron, I call it Fe for ferrum and so on, right? So sometimes we use the Latin names, and sometimes also we use the name of the person who discovered the element. Like for example, I use the curium because it's named after Madame Curie, the lady who discovered the radioactivity. Sometimes we use the name of a country like the Americium or the Americium or the Germanium and so on. Now, there's a very important thing you have to understand. If I tell you that I have something like capital C, capital O, C, O, and capital C and small o, what is the difference between them? So for example, capital C, capital O, and capital C, small o. So the capital C, capital O is the carbon monoxide. It's a compound, but the capital C, small o is the element cobalt. Because if I see the first letter capital, the second letter small, that means it's an element. But if I see capital and capital, it means it's a compound. Like for example here, if you check this table, you will notice that all the time the capital letter is first, the second letter is small, that means it's an element. But if you see CO or H2O, all capital, that means it's a compound. So please be careful about this. Now let's look at the atom, and as all of us know that the atom is the smallest particle of an element that retains the properties of the element. So that's the smallest part, and it keeps the same properties of the element. And as we all know that the atom is made up of a nucleus at the middle of the atom, and then we have electrons that rotate around the nucleus. Now, what is inside the nucleus? We have protons and neutrons. The protons have positive charges and the neutrons have zero charges. And electrons rotate around the nucleus and they have the negative charge. So that's what we see here, that atoms are composed of even smaller particles called the subatomic particles. And what are those subatomic particles? We have protons, we have neutrons, and also we have the electrons. But inside the neutrons and protons, we have even smaller particles. What do we call them? We call them the quarks. We call them the quarks. So each proton or neutron is made up of three quarks. Each proton or neutron is made up of three quarks. So what about the electrons? Are they also made up of quarks? The answer is, so far, we don't think that electrons are made up of quarks, but protons and neutrons are made up of quarks. So let me repeat this one more time, that the atom contains nucleus, and around the nucleus we have the electrons rotating around the nucleus. Now, what is inside the nucleus? We have protons and neutrons. The protons have a positive charge, neutrons have zero charges, but electrons have negative charges. Now, protons and neutrons are made up of smaller particles that we call them quarks. Each proton and neutron is made up of three quarks, but electrons are not made up of quarks. So as you can see, quarks are protons and neutrons are composed of even smaller particles known as quarks. Now, we know 6 different quarks, okay? We know 6 different quarks, and you can go to the internet now and find the name of those quarks. So what are the name of the quarks? We call them up, down, strange, up, down, bottom, up, strange, and I forgot the name of the last one. I will get it now. Okay, I will get it in a minute. So it's up, down, top, bottom, okay, okay, we can check the name of the quarks. So let me see the name of the quarks. Name of quarks. So we have strange, bottom, up, top, yes, sharp. Okay, so the name of the 6 quarks are up, down, top, bottom, strange, and sharp. Yes, strange and sharp. Okay, so let's keep moving. So now I have those 6 quarks, as I mentioned, and each proton or neutron is made up of those 3 quarks. Okay. Now there is something which is called the particles accelerator. It's called the particles accelerator. And what are the particles accelerator? Now, if I want to study those subatomic particles, I want to see what is inside them, what we do is we make them move at very high speed. It means that we are making them increasing their speed or accelerating, right? And then we make them hit each other. So when they hit each other, they split into even smaller particles. Okay, this can be found in the particles colliders or the particles accelerators. So here you can see this accelerator has a circumference of 6.4 kilometers, and that one has a circumference of 27 kilometers. So we call this the circumference, the 2 pi r. So this one has a 27 kilometers. So as you can see here, that for this large distance, we can make like particles like neutrons and protons accelerate on those accelerators, and what happen is they move very very fast, and then we make them collide with each other. So as you can see, they are called particles accelerators, and when they collide at this very high speed, then they split into smaller particles like the quarks and so on. Now here also I have something which is called the wire chamber. It's called the wire chamber, and you can see from the name it's called wire and chamber, right? So chamber means a room, and wire means a room that contains wires. So those wires carry electricity, and what happens is if you have a particle that enters this room, then what happens is it interrupts the electricity, it interrupts the electric current that moves inside this chamber. And then what will happen, each particle will have its own unique feature, and then it changes the electricity inside the room, and then we can identify those particles. So let me repeat this one more time. So if I say it's a wire chamber, a chamber means a room or a container, and this container contains wires, and those wires contains electricity, like electric currents. So what happens is when particles, like charged particles, enter this room, what happens is they change the electricity, they change the behavior of the electric current inside the room, and then what happens is by this change we can identify different particles. So in this slide we need to know two things. We need to know what are the particles accelerators, and particles accelerators are places where we can accelerate particles. We can make them move faster and faster, and then we make them collide. When they collide, they produce smaller particles. And the wire chamber is a container that contains electricity, and when the particles enter the container, then they change the electricity inside this container, and by that change we can identify those particles. Okay, now the next thing we'll speak about here is called the atomic model. And as we know that atoms are very small, and by the way guys, we cannot see atoms. Atoms cannot be seen, and no one ever was able to take a picture or make a photo of an atom, because atoms are very small and we cannot capture them so far with any camera. Nobody ever was able to see an atom. So if atoms are too small and nobody is able to see them, so why do we say that atoms look like that? Why we say that they are made up of nucleus in the middle, electrons that move around the atom, around the nucleus, and so on. So that's what we call a model, because no one was able to see an atom. But what we can do is we can, by experiment and by theories, we can think about how the atom could look like. You know, this is like what? Like I want you to imagine that there is a blind person who cannot see anything, and you ask him to describe a room for you. Now, the blind person cannot see the room, but he can still move inside the room. And once he hits a chair or a table, he will tell you there's an object here at this location. You see the idea? He can describe the room for you, or she can describe the room for you, but it cannot be. He cannot see the room. Now we have like different atomic models, and I want you please to know those models very well. So the idea is you need to know the name of the scientist or the philosopher, and you need to know what is his or her contribution to the atomic model. Now the first person that we need to learn about here, his name is Democritus. And Democritus, based on the textbook, he is the first one, or he was the first one who talked to us about atoms, and who told us that matter is supposed to be made up of atoms. So he said that atoms are tiny particles that make up all matter. So he was by far was the first person who told us about atoms. Now, at his time, there was one other philosopher who was very famous, and maybe you guys heard about his name. His name is Aristo, and Aristo said that Democritus is wrong, and he said that there is nothing called matter and nothing called atom, and he said that matter is uniform throughout and was not composed of small particles. So Aristo said that if you get any substance and you start dividing it into smaller and smaller and smaller particles, you will just end up with smaller pieces, but you will never reach something as an atom. You will never reach something that as an nucleus or electrons or protons and so on. Now, unfortunately, because Aristo was very famous and he used to have lots of respect at his time, so people did not believe Democritus, and they believed Aristo for thousands of years. And at that time, nobody believed that there is something called an atom. Until another scientist, his name is Dalton, he came again and he revived the idea of the atom. Now I want you please to know what are the assumptions, or the what we call it the postulates of Dalton. Now Dalton first said that matter is composed of extremely small particles called atoms. Okay, so this is right? He said that matter is made up of very small particles which we call atoms. Now number two, he said that atoms are indivisible and indestructible. So he said that you cannot divide an atom. So indivisible means that you cannot divide it. Now this is not true, right? Because now we know that atoms can be divided into smaller particles, and we can see it's can made up of protons, neutrons, electrons, and even the quarks. So this assumption was not correct. Number three, he said that atoms of a given element are identical in size, mass, and chemical properties. Now let's see if this is right or not. It says atoms of a given element like aluminum or carbon are identical in size, mass, and chemical properties. Now if you think this is right, no, it's not right, it is wrong. If you guys remember that we have learned before about something called the isotopes. Remember the isotopes from high school. What's an isotope is, like for example, I can think about carbon 612 and carbon 614. Now those are called isotopes. Now these are two atoms of the carbon, but carbon 14 has a larger mass than carbon 12, right? So this assumption of Dalton was not correct, because it could be atoms of the same element, but they do not have the same size, mass, and so on, right? So this is because of the isotopes. Okay, now let's see the next assumption, and it says that atoms of a specific element are different from those of another element. Now this is correct, right? Because the atoms of the magnesium should be different than the atoms of the carbon, then the sodium, and so on. Next thing says that different atoms combine in a single whole number ratio to form compounds. Yeah, this is of course correct, right? Because we know that, for example, H2O must be made up of 2H and 1O, or CO2 must be either it must be 1C and 2O, and so on. Now, lastly, in a chemical reaction, atoms are separated, combined, or rearranged. Now, this is of course correct, right? If there is a chemical reaction, then atoms are combined and rearranged in a certain like they change, right? And so for example, if I think about a chemical reaction between NOH and HCl, sodium hydroxide, and the hydrochloric acid, you can see the atoms will be recombined, rearranged. It makes NaCl plus H2O. NaCl will be the sodium chloride, and H2O is water. So NaOH plus HCl give us NaCl plus H2O. So yes, this is correct. In a chemical reaction, atoms are separated, combined, and rearranged. So as I told you that in chemistry, we need to memorize most of the information. So please, I want you to know the name of each scientist and what is his contribution. Like for example, you have to memorize these 6 assumptions of Dalton. You need to know the contribution of Democritus, Aristo, and so on. Okay, now it's also good to visualize the atomic model. We need to know how the atom could look like. Now you need to know the picture. Now in this picture, I can see the atomic model of Democritus. So that's how Democritus thought about the atom. He thought that the atom looks like this solid ball, and nothing inside, nothing outside. Okay, so as you can see here, Democritus first proposed that elements consisted of tiny solid particles that could not be subdivided, and he called those particles atomos, meaning uncuttable. So he thought that those atoms are very small, they are solid, nothing inside, nothing outside, and so on. Democritus' ideas were criticized by Aristo, who believed that empty space could not exist, because Aristo was one of the most influential philosophers at his time. Democritus' atomic theory was rejected. So here, this is the model of Democritus, and as you can see, his model was rejected by other people at his time, and this is because of Aristo. Now, after him, we have the Thomson model, and Thomson told us that, okay, I will use the Democritus model, but there must be negative charges inside this atom. So Thomson thought about the atom as you think about a watermelon. You think about a watermelon, it has seeds inside, right? So he said that the atom is like a watermelon, and the seeds should represent here the negative electrons. Okay, so that's how Thomson thought about an atom. So that was an English physicist, and he said that that the atom consists of a spherical, has a spherical shape. And it also has small negatively charged particles, and he thought that those particles are the electrons, but they are inside the atom, and they are evenly embedded throughout the positive charged sphere, much like a chocolate chip or a watermelon, as I told you. So think about as the book says, think about a cookie with chocolate chip. So the cookie would be a positively charged atom, and inside this positively charged atom we have those chocolate chips, which are representing the negatively charged electrons. Now, after that, another scientist, his name is Rutherford. And Rutherford, if you remember, he is the one who did the Rutherford experiment, the golden leaf Rutherford experiment, shined a when he shined alpha particles on the golden leaf, and he noticed that most of the alpha particles were able to pass through the gold leaf, but some of them were reflected back. So that's why he said that most of the atom is empty, and in the center, or at the center, there is a positively charged particle that he called the nucleus. So Rutherford used the same model of Thomson, but he said that electrons should not be embedded inside the nucleus, but they should be rotating outside the nucleus like this. So we have a positively charged nucleus in the middle, and then we have electrons that exist outside the atom like that. So as you can see here, the English physicist Rutherford proposed that all positive charges of an atom should be concentrated at the central atomic nucleus, and the electrons are surrounding the nucleus and rotating around the nucleus. Now, after Rutherford, there was another scientist, and his name is Bohr. And Bohr used exactly the same model of Rutherford, but he said that electrons should exist in specific places around the nucleus, and he called those specific places the orbits. So he said that electrons must exist in specific orbits around the nucleus, or fixed orbits around the nucleus, and each one of those orbits should have specific energy. And he said that electrons cannot exist between those orbits. So an electron could be in the first orbit, or the second, or the third, or the fourth, but it cannot be in between these two orbits. And he also added that electrons can travel between one orbit to another if they have enough energy. But if they do not have enough energy, they cannot jump from one orbit to another. Or they can go from the higher orbit to the lower orbit if they can lose the specific amount of energy that he called the photon. So as you can see, this is the idea of Bohr, and he said that electrons traveled in fixed orbits. The electrons could jump between orbits as they absorb or release specific amount of energy. And now the Bohr's model is a very good model and works very well, but it works only with the hydrogen atom. But if you try to apply it on larger atoms, a heavier atom, it does not work very well. So the Bohr's model is great, but it works only for the hydrogen atom. But if you try to apply it for heavier atoms, it does not work. So that's why scientists came up with another model, which is the mostly accepted model right now, which we call the electrons cloud model. And the electron cloud model says that electrons should exist everywhere around the nucleus, and electrons exist in a form of a cloud around the nucleus. So it says that the area around the nucleus of an atom where electrons are most likely to be found. So it means that you try to find the electron anywhere around the nucleus, and these likely places are in a form of a cloud where electrons can exist anywhere around the nucleus. Now we have something called the uncertainty principle, and the uncertainty principle told us that it is difficult to determine the location of an electron and the velocity or the momentum of the electron at the same time. It's impossible to do these two things exactly at the same time. And if you want to understand this uncertainty principle, you can imagine this. Now I want you to imagine that you have a helium balloon. You know those helium balloons that kids like to play with, and I put it in a dark room, a very dark room that you cannot see anything, and I ask you to try to find the helium balloon. Now you cannot see the balloon, but all what you can do is you can walk and try to find the balloon. So you keep walking inside the room until you hit something and you tell me, yes, I found the balloon. The balloon is here. But once you do that, the balloon will move somewhere else. Now you don't know where the balloon now, right? So the same thing will happen if you try to find an electron. Now to find an electron, you need to use some sort of energy to be able to find this electron. But because you use this energy, electrons will take this energy and move somewhere else. That's why it is impossible to find the location and the velocity of the electron at the same time. Okay, so in this lecture, I want you to, as I mentioned, to know the different atomic models. I want you to know the Democritus model, the Aristotle model, the Dalton's model. I want you to know how those models could be visualized, because sometimes we put questions and we give you, for example, this model and tell you this model belongs to whom, which scientist is giving us this model, and so on. Okay, so that's all for today. Thank you so much, and we'll see you in more YouTube classes, inshallah. Thank you.